Hello students, today we are in lecture number 57. Chapter 4 of moving charge and magnetism. Hopefully it is the second last lecture of this chapter number 4, my dear student. We were studying in last lecture about the thyroid, and we left with the derivation of magnetic field due to thyroid. So we'll finish it today. Kindly give the heading magnetic field due to thyroid. This is the core of thyroid. The current, it is in and out. This is the number of turnings in thyroid. Here, my dear student, the radius of the thyroid, it is, suppose, R1 and R2. Alright, these are the radius. We wish to find the magnetic field outside the thyroid, somewhere here, in between the core of thyroid and here inside the free space of thyroid. Okay, so let me find the magnetic field over here. So using Ampere circuitry law, we have to first here draw the Amperian loop like this way. Okay, making the Amperian loop, what we are doing, B due to thyroid. Alright, the thyroid is electric or the electronic arrangement in which we don't get any pole. It has no end pole, that is the south pole and north pole fast to each other. So how it produces magnetic field? It produces magnetic field north pole and south pole over is this fascimals. Okay, my dear student, if we take the point P1 outside and the observation length, suppose it is X, it means we are considering here the case 1, it is outside the thyroid, X it is greater than R2. Alright, it's quite clear from the diagram, my dear students. If you'll see here, the current is moving I in and it is out. Look at here, in this Amperian loop which is drawn touching the point P1, you can see the total current moving in, it is I ampere, but same time this I ampere leaving the Amperian loop. So the total net current that it will be enclosed, I enclosed, it is 0. Of course, B dot dl, this is the length dl, and it is how much, mu naught times I net, it is 0. So the B will be 0. For thyroid, magnetic field outside the space of the thyroid, it becomes 0. Case 2, my dear student, if we consider at any point in between the in between the space of thyroid, okay, somewhere here, the point P1, look, this is the point P2, sorry, it means X, it is less than R2, but it is greater than R1, okay, for point P2. Now here you will go inside this toroid. Let me draw the imperial loop using my red sketch. This one is your imperial loop. All right. So for this imperial loop, you can see, my dear student, either current moving in or out. Okay. So you will get a net current. All right. You will get the net current, and for that we can write here the I net, I enclose, it is I. Now using Empire-Circuital law, we can write B dot dl, it is equals to, since the current having the number of turns n, so it will be the n times mu naught I enclose. I hope you understand, my dear students. Now it is B and dot dl, it is n times mu naught I, the value of dl, it is 2 pi x, it is n times mu naught I. Alright, so this will be the B is equals to mu naught Ni over 2 pi x. This is the magnetic field inside the toroid. Remember, student, the net current here, the passing through inside, all right, it was I, and we have taken n is the number of turn. Okay, so this one is the condition, and here x is the observation length. You can see this x is the observation length from the center. All right, from the center. Now let me find the magnetic field due to this toroid at point P3. Remember, student, this x we generally use the average one. All right, that is the r1 plus r2 by 2. We use the average length. All right, because it had the 2 radius, so we use the 2 radius average. Okay, now the next case 3, here we are going to find magnetic field somewhere here. All right, this is the point P3, and it is x will be less than r1. All right, here again you can see the I enclose, it is 0. If you will make a Gaussian imperial loop like this way, you are not getting any current inside this loop, so it will be I enclose 0. So the B dot dl, it is mu naught times, it is 0, and the B will be 0 as well. And from this result we can conclude the magnetic field due to toroid only exists in this space, as we have discussed in last class. Okay, the magnetic field we don't obtain outside the toroid, in between this free space of the toroid. Actually we get the magnetic field in between the core of toroid. Okay, student, we have studied about the solenoid, but we haven't discussed how the solenoid magnetic field can be increased. Okay, so the solenoid magnetic field can be increased by the various method. All right, by insertion of soft iron core. If you will insert soft iron core over here in the toroid, you will get the high magnetic field. The magnetic field magnitude will be increased, and the rest things are as it is in diagram. By increasing the length, you will find if you keep the turning same, increasing the length, the magnetic field will be decreased. If you increase the number of turning, keeping the length same, then you will find the magnetic field increase. And if you increasing the number of layers of turning, keeping the length same, then you will find again the increase in magnetic field. Okay, so these are the factor, and the more factors are there, you can study, you can get analyzed by yourself, my dear student. All right, now today's next topic. Today we are going to start the next topic. It is moving coil galvanometer. Okay, this is a very important topic, my dear student. Moving coil galvanometer. MCG. All right. Yes, there are a number of galvanometer in our science, but we are focused to the moving coil galvanometer. First of all, you should know what is this moving coil galvanometer. My dear student, inside the lab you will find a galvanometer, okay, a meter over which it is written Z, and that it is used to find the detection of current, okay, to detect the current, the presence of current. Simply you can say that moving coil galvanometer, that is the galvanometer, it is an electronic device which is used to detect the presence, okay, which is used to detect the presence only. And presence of which one? The presence of electric current in any circuit, nothing else. All right, it used to, but this galvanometer can be converted, my dear student. We can convert galvanometer into voltmeter and ammeter. That we will study in our course, and hopefully that will be the last lecture. So let we start today. We start today with the principle and working of galvanometer. So the principle. My dear students, you won't get the principle right now, only you have to write, but after making the diagram, I'll explain this principle. Okay, so the principle is, it works on the principle of torque. When a current carrying coil placed in magnetic field, it experiences some torque. All right, and this is the principle of galvanometer. On this principle, actually you know very well, if you will place a current carrying coil inside the magnetic field, due to that magnetic field, current carrying coil experiences some force. All right, and due to that force it start moving, and due to the motion you can say it experiencing some torque. And this is the principle of galvanometer. Okay, now let me draw the diagram of galvanometer. It is given in your book, the very simple diagram in NCERT. You can follow. Here I am drawing the practical diagram of galvanometer, how it actually looks like. This is a soft iron cylindrical core, okay, and over this cylindrical core a wire, that is coil, winded, having number of turns. The number of turnings are there. This is the coil, and from this coil there will be two end of the wire. One you can see this one, and another is this one. Suppose you used to provide current from here, okay, current moving in, and it is living at this junction, that is at this end. Now, this entire setup, this one, it consists with a spring over here. It is the center tapped spring is connected. This one, it is a spring. It is a spring, and this spring is connected over here, and this spring consists with a pointer. This one, this pointer, all right, and this pointer, it is provided with a scale. There will be a scale on which marking done. Okay, divisions are given for the measurement. This is the scale. Now, this soft iron core having the current, this is insulated conductor wrapped over the cylinder. If you will see the shape of this current carrying wire I have made with the red, you will find it looks like this one. Okay, it looks like this one. And if this is the coil placed in magnetic field, if we apply a magnetic field in this direction, then what will happen? This coil will start experiencing some torque from where it get the magnetic field. So this is the source of magnetic field. You can see, my dear student. This is a magnet. Electromagnet can be also used for this purpose. This one. You can see the two magnets are given over here, and this magnet, it is of such form, this is of such form, they produces magnetic field radial. Okay, they produces magnetic field radial. Why they produce radial magnetic field? If this is north and this is south, why they produce magnetic field radial? So they produce magnetic field radial so that this coil receives uniform magnetic field while rotating. Otherwise, if that will be the straight like this way, and if a circular coil rotating, then at this position the coil having the very large distance, and when it is rotating and it comes to this point, it has very small distance, and due to this distance variation, there will be fluctuation in magnetic field. So it makes like this one. While it is moving, it receives at every point the same magnetic field because it is of uniform magnetic field. Why? Because the separation will be same to this particular cylinder. All right, my dear student. Yes. Okay. Now, the principle of moving coil galvanometer, it was the torque experience. This is the pointer, remember, this is the coil, this is the soft iron core. You can write everything in legend. All right. Now, this pointer, which is attached with a spring, it is made up of phosphor bronze. We use this material to make the spring, that is the phosphor bronze, because its value of torsion constant K is very less. Remember, that's why we use phosphor bronze. What does it mean? The minimum value of K, it means after number of twisting, its dimension, that is the elongation, does not change, and that's why we use phosphor bronze. Okay, if you use steel or copper material for making the spring, after some twisting, the dimension or the structure may be retort. That's why we use that particular material in moving coil galvanometer. Such type of question may be asked in your board examination. Okay, my dear student. Now, we are going to find out here the actual deflection by the galvanometer. Remember, when current move through this galvanometer twists. Okay, it moves, and it moves by certain angle. All right, but it experiences a torque due to current, and how much torque it experiences. So the tau can be written as N I A B sine theta. Theta, since it is the radial, so the everywhere the magnetic field will be perpendicular to this coil, that is the 90 degree, and so it will be the 1. This is the torque experienced by the coil. Torque by coil. You can also write, before writing this equation, torque experienced by coil. Okay, and then after you'll write this equation. Now, if this torque rotate the coil and it has to give the reading again and again from the same point or for the same value, then who is going to come back this coil to its original position? So a spring is going to come back at its original position, and that apply the counter torque. All right, and that counter torque, that is the torque by, or the counter torque of spring can be written as tau is directly proportional to the deflection. Okay, how much this coil is twisting, it totally depends upon this one. If phi is the twisting, you can say it is the angular deflection. Then this tau is directly proportional to phi for the spring, and now tau is equals to k phi, where k is twisting or torsional constant. Okay, and this torque will be equals to this torque, because this torque is being balanced by the counter torque k phi. It is k phi NIAB. So you can find here the deflection. It is deflection. Okay, it is NIAB by k. Now what are the constants value? N is constant, A constant, B constant, and K constant. Okay, so phi is equals to I N A B by K. Actually, this is known as the galvanometer constant. Remember, and then we can write this is GI. This G is galvanometer constant, and then simply you can write phi is directly proportional to I. Now you can see, my dear student, phi, it is directly proportional to I. Okay, let me set the vision. I think my board is going out of the vision area. All right, now look at here. Thus phi is directly proportional to I. Phi directly proportional to I, it means as you will increase the current, the deflection will, phi, what is this phi? Phi is the angular deflection. As you will increase the current, the deflection will increase. Okay, as will decrease the current, the deflection will decrease. Now it totally depends upon, as if you are giving the very small amount of current, it will deflect by very small. How much it will deflect, it depends upon the sensitivity of this galvanometer. That is our next topic we are going to cover here, the sensitivity of galvanometer. All right, so give the heading sensitivity of galvanometer. Sensitivity of galvanometer. you find that for one galvanometer you apply 0.1 ampere and it gives the reading for 10 division. But for another galvanometer you find that you apply 0.1 ampere and it deflects 50 division. So you can say the second one is more sensitive. It means under the small current it deflecting very much one. Alright, suppose if you given a current and one galvanometer does not deflect, it means you can say this is very less sensitive device, that is a very less sensitive galvanometer, because for that particular value it is not giving any deflection. Its sensitivity is very low. Basically the sensitivity are of two types, one while giving the current and while giving the voltage. So the current sensitivity and voltage sensitivity. First, here we are going to study about the current sensitivity. Okay, current sensitivity. It is represented by eta I. Okay, the current sensitivity. This current sensitivity is mathematically defined as the deflection per unit current. You are giving the current and how much it is twisted. Okay, this is called the current sensitivity. Very simple, my dear student. From the given formula you can write here, it is phi by I. So the phi by I can be written as NAB by K. NAB by K. This is nothing but the current sensitivity. Now how can you increase the current sensitivity? You can see increasing the number of turns. As you will increase, the current sensitivity will increase, increasing the area, increasing the magnetic field, and decreasing the value of K. That's why I told you the minimum value of K we use for the phosphor bronze. That's why we use that particular material to making the coil. All right, so N, that is eta, which is the sensitivity. It depends depending upon this quantity. All right, now the second, voltage sensitivity. Voltage sensitivity. My dear student, the voltage sensitivity we used to represent by eta V, and it is mathematically the deflection per unit volt. Okay, per unit volt. Now you can see in this formula how you will get voltage. We know that V is equals to IR, multiplying R both side here and here, you will get the voltage sensitivity from this only, R and R. You will get the voltage sensitivity. It means this will be NAB by K into R. So this is the voltage sensitivity NAB by K R. Now what are the factors that will increase the current voltage sensitivity, my dear student? So we can study here, we can see here, as you are increasing the number of turns, the voltage sensitivity, whether it is increasing or not, let us consider. As you will increase the number of turn, remember, as you will increase the number of turn, it means you are increasing the length. And if you are increasing the length, remember, you are increasing the resistance also, as we know that the resistance directly proportional to the length. It means increasing the number of turn, this resistance will linearly increase, and so there will be no effect on eta V, that is on voltage sensitivity. So remember, by increasing the number of turns, you cannot increase the voltage sensitivity. If the number of turning are same and you are changing the resistance, of course the sensitivity will change. But if you are keeping this constant number of turn, resistance, and if you are changing the number of turn, keeping this resistance constant, of course the sensitivity will change. Otherwise, if the resistance you are not going to disturb, resistance is also changing. All right, as it is increasing the number of turn, so the number of turn will not affect the voltage sensitivity. Area will affect, magnetic field will affect, and K, of course, it will affect. So suppose if you are increasing this current sensitivity, all right, current sensitivity, what it means? It means you are changing the value of NAB by K. If you are changing the current sensitivity, is it necessary that voltage sensitivity will change? Answer is no. It is not necessary that voltage sensitivity will affect if current sensitivity is changing. And this is one of the very important question of the board. Why? Then you have to give the explanation, because the voltage sensitivity contained with the N and R, and both are inversely proportional. As you will increase the number of turns, resistance will also increase, and resultant there will be no effect on the voltage sensitivity. It means changing the current sensitivity is not necessary that voltage sensitivity will change. Okay, my dear student. So this is the moving coil galvanometer. My dear students, in next lecture we will do the conversion of galvanometer into voltmeter and ammeter, and then we will solve few numerical question and will bind up this chapter number 4. Okay, my dear students. So this is all about today's lecture. Thank you very much.